Hello everyone, welcome to the Spintangle. Today, this lecture is completely based on the removal of Gibbs paradox. Okay, so let's make an heading that is removal of Gibbs paradox. The Gibbs paradox is completely based on the Maxwell-Boltzmann statistics and also in case of distinguishable particles. Okay, distinguishable particles in which a problem arises. There are two problems which are related to each other, that if we increase the number of particles by alpha, a factor alpha, and for that the volume will also increase by a factor of alpha. Therefore it was expected that the entropy should increase by a factor alpha, and we have seen that our conventional formula for entropy was irrelevant regarding this thing. Okay, there was a mismatch among this thing. Okay, and that has not matched anymore, that we have seen in the lecture, in the previous lecture. Okay, so let's see how it has been removed. Okay, how it has been removed. So let's start with the fact that what is called the distinguishability. Distinguishability. What is distinguishability? First, let's understand this thing. Okay. So distinguishability means, say there are I'm changing the ink for your understanding purpose. Say you have to distribute. Okay, you have to, this is an example. Okay, you have to distribute three particles which are distinguishable. Which are distinguishable. This means what? This means you can label them individually. Say the particles are labeled as A, B, C. Okay. So the number of microstate will be what? This is our question. What is the number of microstates? In distributing these three particles in, say I'm giving in distribution building these three particles in three boxes. Okay, then what is the number of microstate? What are the, say this is what are the number of microstates in distributing these three particles in three boxes? Okay, let you have three box. What are the three box? Say this is a system in which there are three compartments in which you have to distribute these particles. Okay, so the you can distribute like this, say in this box A, in this box B, in this box C. Therefore this is one microstate. Okay, the internal arrangement. Okay, this is one microstate. Another microstate will be what? Say you can arrange them internally by BSC format. This is another microstate. Okay, say you can organize them as CAB. This is also one microstate. Okay, these are let me level this microstate, number of microstates here. Okay, these are microstates CAV, and also you can level them as say ACB. This is another microstate. Okay, and ACB, and what we can CBA, say CBA, and you can arrange them this like BCA. Okay, this is another microstate, this is another microstates. Okay, so this means what? I cannot rearrange them out of this. Okay, this means there are 6 microstates, 6 microstates. Okay, if there were 2 particles to distribute, say there were 2 particles, if there were 2 particles, 2 distinguishable particles, you may write this thing, 2 particles A and B, and you have to distribute them in 2 boxes. Therefore, say this is the box, and these are the 2 boxes. Okay, say you can arrange them like this, AB and BA. You cannot arrange with any other way. Okay, you cannot arrange in any other way. Okay, this means this produces 1 microstate, and this also produces 1 microstate. The total number of microstates will be what? 2 microstates. So what we can see from this, if you have n, generalizing the fact, I am writing this generally, that so this thing I am using this generally, what we can say from this thing, that if we have to distribute indistinguishable particles, then the number of microstates will be equals to n factorial ways. That means what? That you have n factorial number of microstates or n factorial number of internal arrangements of a particular macrostates. This is for I am writing this thing, this is for distinguishable particles. As the particles are labeled as individually, say you can write them as A, B, C, D, or whatever you can write. Okay, say this is up to, there are n particles. That means say the n particle, now we can conclude this thing. We can say if there are say if there are n indistinguishable particles, this is omega, say level as number of microstate omega, n particle omega. Okay, this is if there are n individual, sorry, in indistinguishable, sorry, indistinguishable particles, that means the number of particles will be what? The number of microstates will be what? Microstates will be equal to omega n upon n factorial. Okay, in case of distinguishable particles, you can check this thing by our examples. Okay, this is what? This is in distributing 3 particles. You have, this means 3 factorial microstates. Okay, in distribution between 2 particles, you have 2 factorial microstates. Okay, in distributing n particles, you have n factorial microstates. Okay, in case of n is indistinguishable particles, there will be number of microstates which is equal to omega n upon n factorial. Okay, this means what? This means indistinguishable particles. I have told it earlier that indistinguishable particles creates no extra arrangements. It means no more arrangements. Okay, arrangements. So we have to divide the number of microstates by the number of particles times factorial. Okay, this is the ultimate thing. Okay, you can see from this thing that you have to divide. Now let's understand this thing. Say you have 2 particles. If these particles are distinguishable, say distinguishable means you can label them, say A and B. Therefore, they will create a combination. This is a combination, say AB, this is a microstate, and BA is also a microstate. Therefore, the number of microstate will be what? 2 factorial, means 2. You can write it 2, but I have written it for the general understanding purpose. Okay, this means now this is distinguishable case. In case of indistinguishables, if the particles were indistinguishable, this means you cannot label them. You just have to say you have 2 identical particles, identical indistinguishable particles. You cannot distinguish them individually. Okay, this is what we call indistinguishable particles. You can distinguish them individually in case of distinguishable particles. Say this particle is A and this particle is B. In case of indistinguishable particles, you are not supposed to choose which particle is A and which particle is B. That means you can arrange them like this particle is in this way, in this place, and this particle in this place. Okay, rearranging these particles, it does not say this particle comes here, say this particle goes here. This does not create any other state. You can see what is this? This is similar to this thing. Okay, that means the number of microstate will be what? Here the number of microstate is given by, say, 2 factorial. So in this case, the number of microstate indistinguishable, say indistinguishable case, what you have to do? You have to divide 2 factorial by 2 factorial. This is the say 2 factorial, not writing this 2 factorial. I am writing this omega 2. Okay, this is omega 2 by 2 factorial. This is what the formula this is what the formula tells us. Okay, that if there are, this is the distinguishable microstate in case of distinguishable particles, and you have to divide this thing by n factorial. Okay, why this is division? Because indistinguishable particles create no other microstates. Okay, and distinguishable particles creates various other microstates, ABC, BSC, CAV. Okay, whatever it is, but indistinguishable particles create same microstates. Okay, that means you have to divide by n factorial to uh, to describe this thing. Okay, this is what we call distinguishability and indistinguishability. Okay, so how Gibbs paradox was removed? How Gibbs paradox was removed? This is the direct answer will be by taking or by considering or by considering the particles as indistinguishable. Considering the particles indistinguishable. In the very statement of the calculation of entropy, it was mentioned that the particles are distinguishable. Okay, so by taking the particles indistinguishable, it has been it has been treated as the most fundamental called, this is called Sakur tetrode relation, okay, or equation, Sakur tetrode equation, the most famous Sakur tetrode equation, which removed the paradoxical situation of Gibbs. Okay, this is not apostrophe s, okay, it's only s. This is what that thing. Okay, so what we can do now, let's start with the mathematics. Okay, what we have to do here, okay, say we have n particle microstate. N particle microstate is given by, say, this is omega n, and omega n will be divided by our previous omega upon n factorial. Okay, what was our previous omega? Our previous omega was given by, this is I am putting this thing on the left side of the right hand side. Okay, 1 by n factorial, and this thing is, what is this thing? This thing is given in our previous calculation. Okay, what was that? V to the power n by h to the power 3n by, say, here it is pi 3n by 2, I think so, it is, I am correct, 2me 3n by 2, and here it is 3n by 2 factorial. I think I am correct in this situation. Okay, this means now this is the corrected microstate. This is the not the corrected, this is the microstate in case of indistinguishable particles. Okay, indistinguishable. This indistinguishable matchmaking has removed the Gibbs paradox. So let's take from this, by starting from this, what we have to do, we have to calculate the entropy in the similar manner what we have done in our previous class. Okay, entropy, how to calculate the entropy? Entropy is given by S equals to k ln omega. Okay, omega n, say in this case it is omega n. So what we have to do here, say this is k, what is ln here? Okay, what is omega n here? The omega n is wait, just wait, omega n is, sorry for the external noises. Okay, some relatives has come to our home, and sorry for this noise. Okay, 1 by n factorial vn by h3n pi power 3n by 2 2me power, I think 2me power, what is this here, 3n by 2, and in the denominator it is 3n by 2 factorial. Okay, now what we have to do, you have to decompose this very big thing, and we will be in our state. Okay, so what is this here? The first term will be k ln in this case say k ln, you have in the denominator term will be in positive ln, and in the numerator term will be in positive ln, and in the denominator terms will all will be in the negative ln term. Okay, there is a k ln vn in the positive side, and in this in the second term will be this. The first term was this, the second term will be what? K ln, say k ln. I am merging this thing. I am merging this thing. I am merging this hn with let me clearly write this thing. Okay, sorry. Let me clearly write this thing. I can write it on the previous manner, that 1 by n factorial. Here it is, and in this term there is a v to the power n, and in this term there is a 2 m pi e upon h square whole to the power 3n by 2, and in the denominator it is, and in the denominator you have to write this thing. Okay, carefully write this thing, 3 factorial. These all things are inside the bracket, and I think I'm done. Okay, so what you have to do, the numerator term will be in the positive ln side. Okay, ln vn. Okay, this is the first term what comes from this conclusion. Okay, so, second term will be what? K ln 2 pi m e upon h square, sorry, not h squared, h square, and to the power 3n by 2, and there will be two negative terms due to this and due to this, because they are in the denominator term, and this denominator term will be with the negative sign of ln. So ln n factorial minus ln 3n by, there is a k 3n by 2 factorial. Okay, I think this is correct. So let's do this thing. Let's carefully disclose this thing. Okay, let's say this is, there will be the first term nk ln v, plus there will be a 3 nk upon 2 ln 2 pi m e upon h square minus k, this k ln n. What we have to do this thing, what you have to do with this thing, you can do this thing with the, let me take this, let me highlight this thing. Say this is the, say this is what you have to do in case of this thing. You have to do so you have to do Starling's approximation you can do. So what will become? Kn ln n minus kn. I think I am correct. Disclose this thing. Okay, and there will be a k 333 kn. So I'm giving a negative sign in that, below. Okay, therefore what does it become? So 3nk by 2 ln 3 ln upon 2 minus 3nk upon 2. I think I am correct, and that here will be a positive sign, and in this term here also be a positive sign. Okay, this nk and this 3nk, these two things will be 5 by 2 nk. I am writing this in the next line. Okay, what does it become? It becomes nk ln v plus nk ln v plus 3. I am merging this thing. So let me merge this thing. Let me merge with this nk ln v and this minus kn ln n. I can write this thing v by n here, v by n plus 3 nk upon 2. Here it is a 2 ln 2 pi m e upon h square. Okay, this vanish, and there will be a minus. I think there will not be a minus sign. Okay, there will be a minus sign, I think so. But what does it become there? Minus 3nk upon 2 ln. I think I am done with this thing. Okay, ln 3n by 2 and this term will merge with this thing, that will become 5 by 2 nk. Okay, so what does it become now? Now I am simplifying this fact. Let me check this thing on my copy. Okay, let me just 1 minute, just 1 minute. Okay, there will be a then what does it become from this thing? Let me just conclude this thing. I can write this thing. How does it can? Okay, this is how does it can. Okay, ln 3n. I think there is a mistake on my copy. Okay, just let me check this thing out. Okay, what can v by n plus 3 by 2 nk ln 4 by n plus 5 by 2. Okay, these two terms merge with each other. Okay, these two terms merge with each other. This means this becomes nk ln v by n plus 3nk by 2 3nk by 2 ln. In the first term there will be a positive 2 pi me by h square, and from this term, these two terms, there will be a common term will be 3nk by 2. This is the 3nk by 2 ln 2 pi me by h square, and there will be a 2 by 3n term because it is on the denominator. It will go on the denominator and will fold it up. Okay, this means 5 by 2 nk. I think I am done from this thing. Okay, now what we have to do, we have to put this thing out here. Nk ln v by n is here plus 3nk by 2 ln. What we can put in this place? We can put this energy term. We can put this energy term. This is energy. Say I am writing this thing 4 pi m by 3n h square. What is E here? E here is 3 by 2 nkt. That was from the law of equipartition of energy. Okay, law of equipartition of energy. In the previous lecture we have discussed on this thing, law of equipartition. Okay, this is comes okay, plus 5 by 2 nk. I think this is done. So this is let me cross the terms and make it more simpler. Okay, therefore entropy will become nk ln v by n plus 3nk by 2 ln. There will, these are the crossing terms. This means this becomes 2 pi mkt by h square. I think I am correct. If I have written any wrong terminologies, you can comment on the comment box. Okay, this is the ultimate secure tetrad equation. Okay, this is the ultimate secure tetrad equation. By using this thing, we can easily remove the Gibbs paradox. Okay, we can easily remove the Gibbs paradox. So let's check the first problem. Okay, I am doing the only one problem related to this thing, and you are supposed to do the second thing from this thing. Okay, this is the famous secure tetrad equation. Okay, so spelling I do not have this. Secure tetrad equation. I do not know the actual spelling of this thing. Okay, so please check this thing out on Google. You may have the Google button, and you can check this thing out. Okay, so let's first check the entropy. Where was the problem on entropy? That if we have, if number of particles increased by a factor of alpha, therefore, and the volume will also increase by a factor of alpha, then S should be increased by a factor of alpha. Prove this thing. Prove this thing. We have taken the previous formula of distinguishable case of entropy, and on this formula we have calculated that here comes a mismatch. Okay, here comes a mismatch, and this means this the previous formula for distinguishable entropy formula was unable to describe this thing. Therefore, let's describe this thing by our formula, or new formula. So put this thing here, put this thing, proof here, put this thing. So what entropy become? In place of n, what comes? Alpha n, k, ln. What comes in place of v? I am writing this from this formula. Okay, alpha v by alpha n plus 3 alpha n k upon 2. Here comes a ln, and there will be 2 pi mkt by h squared. I think this term will not change. Mkt by h square, and in this term 3 by 2 alpha nk. Okay, this is so let's take alpha common from each and every term. They will cross them out. Okay, this term, this means nk ln v by n, and here comes a 3 nk by 2 ln 2 pi mkt upon h square. Here comes a 3 by 2 nk term. Okay, I think this is done. And what you can see from this bracketed term, this is our entropy. This means alpha, say this is s prime. Okay, so alpha s, this means s prime will be what? Alpha s. Okay, this is the removal, this is why the Gibbs paradox was removed. This is a very important conclusion. You may check this thing out, that I am giving a homework to you. Say the actual Gibbs problem, that was that delta S should be 0. Delta S should be 0 for mixing of the same gas. Okay, for mixing of the same gas in a container, that we have did it in our previous class. You have to prove this thing. Okay, let's prove this thing. In the previous class it was coming that this is not plus, this is plus, this is positive. Okay, this entropy change is positive, and you have to put 0 in this positive. Okay, so what you have to do, you have to just use this entropy term, this entropy formula, and calculate the final entropy and previous entropy. That you have a gaseous system, and you have to remove this partition. Before removing this partition, what is the entropy, and after removing the partition, what is the entropy? Then subtract each one. Okay, that comes into account that delta S should be equal to 0. Okay, this is the actual proof of the Gibbs. I am giving it to homework. I have did this thing. This is also the initial problem from where the Gibbs problem was arised, because in our entropy term there was two mistakes. Which are the mistakes? That two, no, there was one mistake, that the particles which have been treated are treated as distinguishable particle. And what you have to do, indistinguishability property of while choosing the particles. Okay, this is the ultimate thing. Okay, so first problem is, say I am writing it, question 1. Okay, what is our first problem? Let you have n spin half particles in a magnetic field B pointing along Z direction, then find number of microstates that N1 particles will be in spin up state. Okay, this is the standard question. So let's understand this thing. This is a problem. Uh, you may resemble this thing with the Stern-Gerlach experiment. Yeah, I think you have heard the Stern-Gerlach experiment. Okay, the experiment that first predicted the spins of the electron. Okay, then spin angular momentums. Okay, whatever it is, Stern-Gerlach experiment. Say this is relevant to the fact. I'm giving the Stern-Gerlach experiment idea. Okay, so what you have to do, say you are giving a magnetic field towards Z direction. Say this is B vector equals to B0 Z cap. This is the magnetic field, only one component that is along Z direction. Okay, there what will happen, that some particles will be in this direction. Okay, and say this is, and there will be another orientation. This is the orientation of the spin plus half. Say this is the orientation of spin minus half. Okay, this is the thing. I think this is correct, and this means this is by spin degeneracy. Okay, spin degeneracy is what? Spin degeneracy. Spin degeneracy comes when a spin system is placed in a, say you have some particles. Say you have some particles. Okay, say you have some particles and you are giving a magnetic field like this. Therefore some particles will go on this direction and some particle will move on these directions. This is the spin degeneracy. Okay, this is the spin degeneracy. They all have same energy state, they all have same energy, but they are different of states. Okay, they are different states. Same energy having different states having same energy are called degenerate, and this is the result of spin degeneracy. Okay, what is spin degeneracy? Spin degeneracy is given by 2s plus 1. Say electrons, say spin half particles. It is given in the question that the particles are spin half. That means how much are the degeneracy? This is 2 times half plus 1. This means what? This means 2. That some particle will be in the up state and some particle will be in the down state. Say I am giving that there are total n particles and n up. Say this is the up symbol, the number of particles which are along the positive half, and the down particles which are in the downward direction. Okay, say this is minus half h cut. Okay, this means spin up particle. The ms value of this thing will be what? I am not, this is quantum mechanical. Okay, this is not a quantum mechanical problem also. ms value of this thing will be say positive h cut upon 2, and this thing is negative h cut upon 2. Okay, this is negative h cut upon 2. Okay. So there will be two orientations of the spins. This means, say this is statistically treated that n particles have n up particles and n down particles. Therefore there is a binomial type relation. There is a binomial type relation. Therefore number of microstate will be what? Number of, number of microstates when n1 particle, n up particle is chosen from n particle. We have seen in the probability lecture that what has to be done in case of if you have to choose n up particles from n particles, this choosing will be done by NCR method. Say here this is up, n up. This means what? This means this is what? N factorial upon n up factorial, and there will be a n minus n up factorial. Okay, this is the total number of microstate in choosing n up particles from a system of n particles. Okay, this is the number of microstate. Okay, this is the answer. This is the answer. Okay, say the part B says part B. This is the previous one. Say this is part A. Say this is part A, and the part says what is the part B? What is the entropy? What is the entropy of the system? Entropy is given by S is equals to K ln omega. This means you have the omega here. This becomes K ln. I'll put the omega from the above formula, that n factorial times n up factorial n minus n up factorial. This is the answer, but what you have to do Starling's approximation for better result. Okay, you have to decompose this thing into it and use say I'm doing this thing. K in the very outside. This means ln numerator term goes with positive ln and the denominator term goes with negative ln. This means factorial minus ln n minus ni factorial. This turns into what? This turns into, say, K in the very outside. By applying on this term, the Starling approximation makes this thing as n ln n minus, this is not I, this is up, ln, what has, okay, sorry, just put, these are the factorials. Okay, this is n up, and this is also n up. Okay, so minus n, this is comes from the first term, a negative sign, and there will be another Starling approximation, n up ln n up minus n up, and there will be in this term what becomes here, so n minus n up ln n minus n up minus n minus n up. Okay, this is the conventional Starling approximation. There is a minus sign. Sorry, not closing this. There is a minus sign. So this means here comes cross terms. You can check this thing out. Okay, you can cut this thing with this thing. Okay, whatever it is, you can cut this thing. Okay, so let's check this thing out. It is your task to do this. Okay, this is the entropy. Okay, up to this thing, this was an important problem, and I will be discussing some more important problem. Let me check some more important problems related to these things, and whenever the problem will be sorted, I will be given I will give some separate videos related to these topics. Okay, so thank you. Up to this thing is okay. I think I'm done with the microcanonical ensemble, and from the next lecture we'll be discussing on canonical ensemble. Okay, and microcanonical ensemble is very important related to various competitive examinations. So share the video among your friends, subscribe the channel, and like the video.